Large language models possess extraordinary generative capabilities, yet they are constrained by a strict mathematical boundary. Their parametric memory is entirely frozen. Before modern architectures, engineers relied on rule-based statistical processing and recurrent neural networks to parse text. These early models processed data sequentially, creating a severe sequence bottleneck, where information inevitably degraded across long contexts. The attention mechanism bypassed this limitation entirely. By allowing the network to process entire sequences of data in parallel, it enabled models to scale exponentially without losing context. This model shows the complete transformer architecture. Data flows from the embedding layer up through a stack of encoders, mapping context, and into the decoders. Inside these layers sits self-attention. 3 distinct vectors, query, key, and value, multiply, explicitly weighing the contextual importance of every word. Because the data is processed simultaneously, the model relies on positional encoding to retain the exact sequential order of the text. Layer normalization is then applied to stabilize the mathematical gradients as they pass through the network. But language cannot enter this architecture directly. Raw text must be fractured into machine-readable numerical tokens using algorithms like byte-pair encoding. Those tokens are translated into embeddings. This high-dimensional space visualizes that translation. The architecture determines semantic relationships through cosine similarity, measuring the exact geometric angles between data points. Concepts with related meanings are plotted physically closer together. Transformers successfully map human semantics into mathematical space, but because this knowledge is entirely parametric, it is permanently locked at the exact moment the training phase concludes. It cannot learn new facts without being rebuilt. Building a foundation model requires an immense compute pipeline. Thousands of GPUs operate in parallel across distributed clusters, continuously adjusting billions of weights via backpropagation. Rerunning this process to update the model's knowledge with new information requires millions of dollars and months of processing time. Continual retraining is an economic and computational impossibility for enterprise applications. The solution is parameter-efficient fine-tuning. Techniques like low-rank adaptation, or LoRa, freeze the massive pre-trained weights and introduce a tiny, low-rank decomposition matrix. The model learns specialized tasks by updating only this fraction of parameters in real time. To ensure the outputs remain safe and useful, the model undergoes alignment. Reinforcement learning from human feedback and direct preference optimization apply reward functions to heavily penalize toxic or inaccurate generation. During inference, generation speed faces new bottlenecks. The KV cache stores previously computed key and value vectors to prevent redundant calculations, while temperature and top P parameters dictate the mathematical probability distribution of the next selected token. Through prompt engineering methodologies like chain-of-bot or React, developers can force the model to allocate a larger share of its compute tokens specifically to logical reasoning steps before outputting an answer. Even with optimal fine-tuning and rigorous prompt engineering, the model faces a hard boundary. It cannot reason about proprietary enterprise data or current events that were never included in its original training corpus. Retrieval-augmented generation bridges this gap. By attaching an external, non-parametric memory source to the model, RAG provides verified context at inference time, mitigating hallucination and bypassing the frozen knowledge barrier. The framework evolved rapidly, moving from early 2017 search pipelines into the modern state-of-the-art architectures used today. This equation defines RAG. It fuses the retriever's fetch probability with the generator's conditional probability. The vector RAG pipeline executes this across 4 stages: chunking raw documents, translating them into vectors during embedding, storing them in a vector database, and finally rescoring by a re-ranking model. In enterprise deployments, the primary engineering failure occurs at the very first stage. Naive chunking strategies arbitrarily slice documents, destroying vital semantic context before the language model ever sees the text. This visualization tracks intersection over union scores across chunking strategies. A rigid 1024 token split degrades retrieval quality, failing against the sentence splitter. With a 512 token window and 200 token overlap, sentence splitter dominates by respecting linguistic boundaries. The overlap lets context bleed into adjacent chunks, ensuring the retriever captures complete concepts. When empirical chunking strategies supply a high-quality retrieval pipeline, generative demands drop. A highly efficient small language model can process this clean context and outperform a massive trillion-parameter foundation model. Pure vector RAG relies strictly on nearest neighbor semantic search. When queried with multi-hop reasoning tasks or highly dense financial terminology, isolated vector embeddings fail to connect the necessary dots. Graph RAG replaces these isolated text chunks with knowledge graphs. This structured approach maps data into explicit conceptual nodes, connected by strictly defined relational edges. Hybrid RAG merges these two domains. It combines the broad semantic matching of dense vector embeddings with the deterministic traversal of sparse graph networks, guaranteeing highly accurate context extraction. When this retrieval mechanism is coupled with autonomous planning and continuous memory, the architecture evolves from RAG into agentic AI. These systems can independently formulate multi-step objectives and iterate based on environmental feedback. Through function calling, the agent writes code to execute external APIs in real time, allowing it to manipulate databases, trigger workflows, or scrape live web environments. To scale this capability across thousands of tools, strictly as the CPU, it is a reasoning engine routing logic through an expansive network of external memory and functional tools. Moving this architecture from a local developer's environment into a globally distributed enterprise data center introduces immense infrastructure complexity. A single user prompt must hit an API gateway, pass through an AI guardrail node for security screening, and finally route into an LLM orchestrator to dictate the execution path. This entire stack is absolutely dependent on CUDA architecture, utilizing frameworks like Kubernetes or Ray to manage workloads across massive distributed GPU clusters. To maximize inference throughput, serving engines like VLM and TensorRT LLM utilize page detention. This mechanism dynamically allocates memory blocks, eliminating memory fragmentation and ensuring a continuous, uninterrupted data flow. Enterprise cost optimization requires further engineering. Prompt caching stores frequently used context in memory, while quantization compresses 16-bit floating point weights down to 8-bit or 4-bit integers, drastically reducing VRAM requirements. Gateway systems utilize model routing to control compute expenditure. Routine tasks are automatically routed to highly efficient small language models, reserving expensive frontier models exclusively for complex reasoning. Scaling an enterprise AI deployment requires solving a latency and infrastructure problem. The machine learning model itself is only one component within a highly optimized serving stack. Because compound AI systems autonomously execute code and connect to external databases, they introduce severe security vulnerabilities. Prompt injection, data poisoning, and unauthorized API execution pose direct threats to enterprise networks. State-level actors are formalizing defenses against these vectors. The 2026 U.S. Executive Order 14409 outlines specific mandates to harden national security systems against AI-enabled threats. The order directs the Treasury Department and the Cybersecurity and Infrastructure Security Agency to establish an AI cybersecurity clearinghouse, prioritizing vulnerability patching across critical infrastructure. It enforces a mandatory benchmarking process for covered frontier models, requiring developers to subject their architectures to rigorous federal red teaming prior to public deployment. Responsible AI engineering shifts from an abstract concept to a concrete technical requirement. Bias, toxicity, and copyright infringement are strictly managed through dataset-level filtration and rigid alignment constraints. Moving forward, the architecture is expanding into multimodal AI. Models natively process text, computer vision, and audio simultaneously, fusing these distinct data types into a single unified latent space. This multimodal capability establishes the foundation for physical AI. The models serve as the cognitive reasoning engines for autonomous robotics operating in dynamic, real-world environments. The transition from isolated, static models toward modular architectures is driven by the demand for verifiable factual grounding and real-world tool execution. Future systems rely on this secure orchestration to bridge the gap between abstract reasoning and reliable performance.